We can start with that.
Okay, I think we can get started. So good evening, everyone. Thank you so much for joining in. And welcome to the Nakshatra community if this is your first event. And if you're new to the community, Sagar will be posting a couple of links to either Telegram or WhatsApp, whichever you're comfortable with.
This girl is good though.
I signed up for 15 people. 15.
Okay, sorry. I think there was some disturbance. Yeah, so again, welcome to the Nakshatra platform. We are basically a collaborative platform for, project-based learning. Our core philosophy is to teach different concepts, some at a beginner level, some at a more advanced research level, but to do all the teaching through the act of problem solving or working on projects. So for the last 3 years, we have conducted more than 40 batches of students who've learned various different things. But in the process of learning, some amazing projects have come out of the community. We really believe in collaboration. So this is definitely a cross-institutional platform. As you will see in the mentor panel, over the next 3 days, we have talks from PhD scholars from various different institutes. So our community is quite diverse in that sense. We also run programs in multiple domains. So this is not an astronomy only platform. We have physics and applied physics. We have explored mechanical engineering projects. We have also looked at data-driven applications. And also, if you've joined in right now, I request everyone to please keep your microphone muted because our class will be, the talk will be starting in a couple of minutes. Okay, Sagar, if you have a maybe an option to mute everyone except the host and the co-host, please see if that option is available. We are having quite some disturbance. Okay, so back to the point. We have today with us Kshitij, and he's doing his PhD in Indian Institute of Astrophysics. Some of you here are obviously participants of the astrophysics course. So I just want to do a really quick introduction to the project that's happening right now. So roughly around, I think some of the participants here are part of something called the mathematical modeling project. And over a span of around 8 weeks, they have been listening to, research scholars from different parts of the country, but also will be working on a project related to star formation at the end of this program. So these cohorts happen on a quarterly basis. So every 2 or 3 months, we launch a cohort and we take in a limited set of students. So if you'd like to register for the next round of projects that we have, please look up the link. We are basically on learn.nakshatra.com. It will start on August 1st, and it will be another 8-week program, bringing together different, research scholars from various institutes and also exploring quite a few different projects this time. So we have radio astronomy in mind for sure as one of the domains of the project. And we will also be looking at other observational astronomy techniques in the projects. Okay, so a little bit about what I was saying. We have basically done a lot of projects related to even data-driven applications in real-world problems. For example, we've picked up a problem in something like climate sciences and figured out how we can approach it from a more scientific point of view. So this is something we do throughout the year. So if you are here in this call and if you're also looking for opportunities to mentor other students, that is if you're masters and above, you can write to us as well. We are available on all the community platforms. And last but not the least, Nakshatra is involved in a wide range of outreach activities, that is offline programs in things like stargazing and building radio telescope workshops and so on. So if you have any inquiries about these workshops for colleges, please again write to us at connect@nakshatra.com. We usually partner with student clubs in various universities, and we've been providing these workshops offline, usually involving something very practical and hands-on. So if you'd like to host a workshop for your university or college, you can get in touch with us. Okay, so finally, I would like to thank Kshitij for being here today. He's actually working on something very, very interesting at Indian Institute of Astrophysics. And if you are aware of one of the observatories under IAA is in Gauribidanur, which is about 100 kilometers from Bangalore. And it's completely a radio observatory. So Kshitij works over there and is looking at pulsar detection, and his recent work is really interesting. So I would urge all of you to also interact with him, but don't unmute in the middle of the presentation. If you can put your questions in the chat box, we will definitely address it with the speaker. And also the last maybe 15 minutes of the talk actually will be kept aside for you to directly interact with him. So feel free to put down any thoughts or questions you might have. One last thing is Kshitij actually comes from an engineering background. So he did his engineering, after which he has pursued an integrated master's, and of course is completely into astrophysics. Of course, he calls himself, I think, astro engineer. So if there are some of you in the audience today who are looking to transition from engineering to science or to some other research domain, it may be helpful for you to ask the right questions today as well. So with that, Kshitij, we can get the evening started. Thank you.
Thank you, Sagar and Sitara. Yeah, I'm audible?
Yeah, you're audible.
Yes, great. Okay, so hello everyone. Thank you for joining. I'm Kshitij. I'm a PhD student at the Indian Institute of Astrophysics, and I'm working in the field of radio astronomy, where I'm building a radio telescope essentially. So today I'll be talking about essential techniques in radio astronomy, and this is a really good time to talk about, because recently you might have seen all these news which I have put in my first slide itself. There was a big announcement regarding some gravitational waves detected, and in this detection they actually used some radio telescopes, so which was different from previous gravitational waves detection, which used something called as LIGO detectors or laser interferometers. So this talk, the radio astronomy is quite getting popular in just about 2 weeks now. It had lot of news articles and everything coming up, so it's a good time to talk about it. And in today's talk, I'll be basically just giving you an overview of what are the different concepts and techniques in the field of radio astronomy, because of course it will be completely impossible to give an entire and what is covered in radio astronomy within an hour, because it itself is a course by which might take about a semester or so, or even in that time you cannot have all the techniques or all the concepts understood. So what I'll be giving you instead is just a flavor or just a taste of this field, so that you might get enticed by it and may come for more later. Yeah. So and hopefully I'm able to excite some of you or intrigue some of you to learn more and understand more or get more involved in this field. Okay. So so I'll be talking just briefly about different techniques that are used and what essentially is radio astronomy. Okay. So let's just start with it. So wait, I'm not able to go ahead. Are my slides moving forward?
No.
No, wait, what happened? Now?
Yes.
Yeah, okay, great. So let's just start with, first of all, what is radio astronomy and all this. Before going into all those technical and physical details, let's just see what radio can give us. So as Sitara mentioned, I'm doing my project at a place called Gauribidanur Radio Observatory. This is a place about 100 kilometers from Bangalore, and it's a nice place for stargazing, because it's away from city, so you don't have a lot of light pollution, and night skies are really good here. And so this is one photo I captured here some time back. And those who are familiar with the night sky might see some familiar constellations, such as you can see here. Is my cursor visible?
Yes, yes.
Yeah. So you can see some familiar constellations such as Scorpius. This is a Scorpius. This is the tail of the scorpion. and there is Sagittarius constellations here, and this is the, of course, Sagittarius arm of our Milky Way galaxy, which if you're living in cities, you might not have noticed ever, but if you have done stargazing at some remote or through your villages, you might have noticed this Milky Way band. So this is what I captured through my mobile phone, and you can see some pretty nice, pretty stars and constellations and everything. But what if this image was taken by a radio telescope? If such an image to be taken, you require some different techniques. We will get later into that. But there is a radio telescope VLA which has actually captured such an image, and it looks like this. In first glance, you will see a lot of differences. So this is basically a composite images. On the background, you can see the stars, which you usually see, some of the bright stars here. But in the center, where there is this Milky Way band, at the center you see this very bright spot here in between. And there are some other details, other structures that you see, which you don't see at all here. There is no presence of any such details, but here you can see some filaments coming out, some other prominent structures here and there, and which is spread over this entire image. So this is basically the essence of radio astronomy. It is showing you something which is invisible to our human eyes, or even cameras, which basically work in optical wavelengths. So radio is apart from that. Radio is something different. Radio is not giving you what is visible, but it is something which is invisible to our eyes. So that is the advantage of radio astronomy. And before now, again, just going into how this image is captured over this course of an hour, I will tell you how this image is captured, how this image is made, and what else can be done with it. But before going into this, let's just start with a brief history. So how we have come here, it is very important to understand how we have come here to this stage where we are able to make such radio images or do such miraculous things with the field of radio astronomy. So a brief history is, of course, it started with Newton. I think no talk on science or rather physics is complete without mention of Newton. So here also Newton started his journey, where Newton, in one of his so many endeavors, he also endeavored in optics, and he made different lenses and mirrors and so on. And he worked with prisms, and he passed a white light through a prism, and what he noticed is these 7 colors that we usually see, we associated with rainbow, the Vibgyor colors. And that essentially started as something new in the field of physics, that the reality is not as we see. White light is not just white light; it is actually made up of different colors. It is a continuum made up of different colors, which together gives you white light. So this Newton started, and later William Herschel discovered something called as infrared light. Infrared light is now light which is not visible, but it has effects such as heat. And now this opened a completely different realm of physics, where now it is not just visible, but there are some things which are invisible, but which do have some physical properties. So William Herschel discovered infrared light, and then Hans Ørsted, what he noticed is electric current produced magnetic field. Now, before that, electricity and magnetic field are two different fields, nobody associated with them. But after this experiment of Hans Ørsted, where he put a compass near a circuit where electric current is flowing, he noticed that the compass actually moved. That means that the electricity was actually producing some magnetic fields. And after this, the field became known as electromagnetism. And Michael Faraday, of course, then noticed something completely different. What he noticed, the light itself has magnetic properties, or electromagnetic properties rather. So now he passed a polarized light through a magnetic field and noticed that polarization changed. So even light showed electromagnetic properties. Now that was completely unexpected. And then came Maxwell, the famous for Maxwell's equations, and Maxwell's gave a mathematical proof that whatever the light or whatever other radiations that we are seeing are basically all electromagnetic waves which travel with the same velocity, which is the velocity of light. And what they have is they have different wavelengths and different frequencies. So that's what essentially separates different kinds of waves, what we call as optical, infrared, ultraviolet, X-rays, gamma rays. All these different kind of waves are part of a same spectrum known as electromagnetic spectrum, and they are having different wavelengths and different frequencies. This till now this is all theory, but then in Henry K. Hertz and what he did is he he generated electromagnetic waves which is using something called as LC oscillator circuits. So using an electrical circuit, he generated electromagnetic waves and also received using a small antenna, which is known as a dipole antenna, and received it and actually recorded the velocity, calculated the velocity of this wave and proved what James Clerk Maxwell had mathematically given that these all electromagnetic waves traveling with velocity of light. So it was true that he proved Hertz proved this, and on his name these waves were known as Hertzian waves, are now presently known as radio waves, and also Hertz is the unit that we use it for to denote frequency. And then Marconi came. Marconi, what he did is Marconi was essentially established how present day radio communication happening. He generated and transmitted and received radio waves over huge distance, over distance of 2 miles, using antennas and receivers and so on and transmitters. And he started something called as telegraph, which basically later came to known as we are having radio communication or mobile communication or even Wi-Fi. Everything is based on this. So he essentially started this new field of radio communication. And then after 1800s, when we entered into 1900s, the radio communication it was used for, first of all, communication and also radar application, radar defense applications, and so on. So radio communication and radio waves gained lot of weightage during this era, and there was a lot of progress happening. But one day in 1931, so this is one very interesting story. In 1931, there was a young engineer working in Bell Laboratories in USA. His name was Carl Jansky, and he was tasked with identifying thunderstorms and what kind of signals they produce. Now, because during this time, the shortwave communication, this is the communication which happens at very low frequencies, it was affected by the thunderstorm, or whenever there is some lightning is there, which has lot of charged particles going around, so which it interferes with the communication. So he was tasked to identify when a thunderstorm is coming and what effect does it have on the communication. So to do this, what he did is he built a rotating antenna and to detect arrival of thunderstorm at a very low frequency, around 20.5 megahertz. And what he noticed, so this is the antenna here, is basically has lot of metallic wires which he can rotate in certain direction to identify any radiation from a thunderstorm coming. But what he noticed, apart from the noise which was generated because of these thunderstorms, there was another steady hiss of an unknown origin. He couldn't find what was the origin of this steady hiss. If you want to, like, if that steady hiss is similar to when you're having a radio, if you turn on an FM and you tune into some random channel, you will kind of sound, you will notice it. So this is kind of noise he was hearing. And there was no explanation for it from where it is coming, but he found out it is coming from a particular direction in the sky, and it is coming at particular time of the day. It was following the time of the space. It was following the time of the celestial objects, and he did a lot of research into it, and finally it turned out to be the center of our galaxy. And this was the beginning of something completely new, and this basically gave the birth to the field that we call as radio astronomy, where radio waves not only using for radio communication or radar application or any other applications, we can actually study the radio waves which are coming from space, and this gave birth to the field of radio astronomy. And this tells, yeah, so this is essentially, we are coming to the field of radio astronomy now. So radio astronomy is the study of radio frequencies, which are 10 megahertz to 1 terahertz frequencies. And what we study is, we study radio waves coming from celestial objects, the objects which are outside the bounds of Earth. And we study stars, galaxies, dust clouds, even planets. So they emit radio waves, and we gather them and we study them. It involves thermal, which thermal emission is because of kinetic motion of the atoms and molecules. So it generates heat, and because of that we get some radio waves. And also non-thermal emissions, which are usually associated with magnetic fields, such as synchrotron emission. So whenever particles moving are accelerating or they are changing direction, they give rise to radio waves, and which we can detect. And the dominant sources of the radios in the sky are the sun. Sun is a huge source of radio waves. There are some supernovas. There are some radio galaxies. The radio galaxies are the galaxies in the center of which we have supermassive black holes, which are emitting some jets. and so on, which we can be detected. And pulsars are there. Pulsars are different types of star, which I will talk later more into detail about it. And so with this kind of radio astronomical studies, what we do is here I have shown some images where we make some maps of the night sky. So this is the map of the, again, our Milky Way galaxy. There are some galaxies that we can see with this, and you can see some jets coming out of it. You can see sun and its magnetic field. You can see some this kind of things. Your pulsar, where signal is pulsating over time. So we can do all these different types of studies. There are some frequency domain studies. For example, we can study something called as 21 centimeter line, which is generated by neutral hydrogen when there is a spin happening. So all this variety of studies are covered in radio astronomy. And so this is the so-called electromagnetic spectrum that I was talking about. So we have a lot of different kind of waves, and our optical, that what we see is a very small part of this complete electromagnetic spectrum. It is a very small part, as you can see here, which covers our optical or our eyes that can detect. But apart from that, there are these different types of waves, which essentially are just electromagnetic waves having different wavelengths and different frequencies. So higher frequencies are having higher energies, so that constitutes gamma rays, X-rays, and low frequencies are basically radio waves. And now by a chance or by something else, we are lucky to actually have this kind of something which is called as a radio window. So now what happens is this diagram essentially tells us sitting on the surface of the ground, what waves reach to the ground and what waves are basically blocked by our atmosphere. So you might be heard that ozone layer reflects the ultraviolet. Similarly, there are some other molecules, for such example water molecules, which reflect other waves. So these waves actually don't reach to the surface of the earth. Only what we reach is there is optical wavelengths which are reaching towards her, and also those are also disturbed by the atmosphere, which with an effect of scintillation or called as twinkling of the stars. So that effect is there. So all other rays, gamma rays, X-rays, ultraviolet, infrared, all other things are blocked by our atmosphere. So that's why you might have noticed that whenever we are having any X-ray telescope or an infrared telescope, we are having this recently James Webb Space Telescope was launched. This is an infrared telescope which was launched in space. Why didn't put it on Earth? Why it was launched in space? To do the observation, because these rays are not reaching our Earth. They are blocked by our atmosphere. But fortunately, radio waves as you can see here, are completely unblocked by the atmosphere. They are directly coming towards Earth without any problems. Now, why this happened, Lord? There are a lot of physics that goes behind it. Why this is happening? But fortunately for us, the radio waves are completely unblocked by our atmosphere, and so that we can study them. So if there is a God, he really wanted people of Earth to do radio astronomy. That's why he might not have allowed these radio waves to be blocked. So what are the advantages of radio telescope? We can see the invisible. As I mentioned, there are so many things which are not visible to us, but a radio telescope can capture them. We can see colder objects which are like gas and dust, which usually don't emit much in optical or other wavelengths, but in radio wavelength they emit a lot. We can have understanding of such as what is the temperature of an object, what are the magnetic field, or what is the composition based on what is the signal that we are getting. And also radio waves are again as they're not blocked by the atmosphere, they're also not blocked by the interstellar dust or interplanetary particles. It does have some effect on it, but they're not completely blocked. So even if there is a sheet of dust in front of some object, radio waves can still penetrate through it and we can see it. And we can do it at day or night. During daytime you cannot do other type of astronomy because sun's light is basically covering everything. But even in presence of sunlight, we can see some other radio objects which are actually stronger than radio wavelengths than sun. And as I mentioned, they are also reaching the ground. So we are having we don't have to put radio telescope in space. We can build bigger radio telescope here itself on Earth. We don't need to go to space. Of course, there is a little there is a cutoff where at low frequencies around below 10 megahertz frequencies are not coming because of the atmospheric cutoff, and higher frequencies are also not coming because of water vapors. But in between, we are from 10 megahertz to 1 terahertz. We have a good big nice window of radio waves that are coming to us. And here is an example of what radio can give. So this is on top panel, you are seeing an image taken by Hubble. It is an image of Cygnus A, which is this radio galaxy very far away. And you can see this at the center of this is the Cygnus A galaxy, which is a very bright galaxy, and there are some other stars and everything here. Now this same object, same field of view, when covered through radio, it's something looks like this, which is another image by a very large array VLA telescope. And you can see here, this is the same field of view, which is now at the center of this. You're seeing the galaxy Cygnus A, and here you're seeing something coming out of it, which is not at all visible here. Now this coming out, the thing is this: these are something jets which are coming out of it, which is because of the mass accreting to the center of the galaxy, which hosts a supermassive black hole. Now, because of this, the things are coming out, these jets, which are spread over about half a light years away, but we are not able to, 500,000 light years away, but we are not seeing it here. But with this radio, we can see it. So now this is the advantage of radio, where then you can study a lot of, it can give you insights of what are the processes and happening inside this galaxy, and what gave rise to such kind of jets. Here is another example. Here we are seeing a couple of galaxies present in this field of view. But when we are seeing in optical wavelength, we are not seeing much details. We are just seeing some galaxies and some other stars. But when we see same thing in radio, what we are seeing is there is an interaction between these galaxies. Okay? If you see here, there is a mass being accreted from these galaxies to this bigger galaxy, which if we see in only optical, we won't be able to see because it is very faint. It is not giving any optical emission. But in radio, it is giving some emission, which is why we can study how this mass is being accreted and how this galaxy mechanism is happening. So this is the advantage. And just a side note, whatever colors that we are seeing here are not actually true colors, because radio waves doesn't have any colors. They are not detectable to our eyes. Our brain doesn't interpret into any colors. So what we have is a false color. So what it is happening here is scientists assign colors based on the different parameters, such as, let's say, this part where there is a huge intensity of radio waves coming, we assign red colors to them, and from where there are not much radio waves coming or less intensity radio waves are coming, we assign blue color to them. So it's a false coloring, and that's how we are getting this image. So similarly, there is an image of sun. So when we see at the sun, don't see sun during normal daytime, but whenever we are seeing during sunrise or sunset time, we see sun as a quite some yellow color or orange color ball. But actually, sun is very dynamic. There is a lot of activities happening on sun, so there is something called as sunspots which develop on sun. And when imaged through a radio telescope, we see how intense they are and how they are emitting, and we can see their shape and everything. And by the way, there is a sunspot presently on a sun, which is even visible without any telescope. But please, whenever you're looking at it, use something called as solar filters, because you should never look at sun directly with your naked eyes. So, or even if you're using a telescope, put a filter on it and try to see the sunspot, which is a huge sunspot, which is visible to naked eyes. So try to see it. So when we see this through radio telescope, we are seeing some such activities happening on sun. And this is an image of, this is a very high resolution image of our galactic center captured by Meerkat telescope, which is in South Africa. Now, again, when you are seeing so many details here, you are seeing these filaments coming out, you are seeing this globular objects here, and so many details which usually in optical or in other wavelengths are not that much prominent. But in radio, you can see so many beautiful details out of it. So now we have understood what radio astronomy can do, understanding what seeing in radio can give you. Now understand how actually it is done, how actually a radio telescope works. So like any other object, like any other telescope, to gather waves which are coming from such a far distance, we need a telescope. A radio telescope is something different from a traditional optical telescope, which has lenses and mirrors, where what we have here is essentially an antenna. Now, antenna is basically a metallic structure which vibrates according to the electromagnetic waves that are falling on it, and it gives some voltages which is in tune with the waves falling on it. So that is an antenna. Antenna is basically a transducer which converts this electromagnetic wave to electrical signals. And we need an antenna as well as a receiver. The receiver is something that will amplify those signals and it will detect those signals, and these signals later can be recorded to study further. So a radio antenna, a radio telescope is similar to your satellite dish TVs. So we have a big dish here, and on this dish, it's a parabolic dish, and on this dish we have a radiation, electromagnetic radiation falling on it, and it will reflect and it will focus on its tip or a focal point where we have kept our antenna, which is a metallic structure which will give the corresponding electromagnetic waves converted to electrical signals, which further we will amplify using amplifiers and other circuits. We will filter them, and we will be recording them on computers using something called as analog to digital converters. Now, so this is the voltages that are induced by this radiation from the cosmic sources, we call it signal. So from now on, whenever I will be referring to anything called as signals, so you have to understand what I mean by signal is basically the electrical signal which is generated by such radio telescope. Okay, so now this radio astronomers use a quantity called flux density to basically tell how strong the radio signal is, and this flux density is represented in terms of unit called as watts per meter per hertz per Jansky. Sorry, watts per meter square per hertz, which is known as Jansky, which is from the father of the radio astronomy field, Carl Jansky. So this Jansky is 1 Jansky is 10 raised to minus 26 watts per meter square per hertz. You can imagine how small this is. Like even our small light bulb or like LED bulb, it has 5 watts to 10 watts rating. But we are talking 10 raised to minus 26 watts, which is insanely small amount of energy. This is and typical radio sources are in terms of milli-Janskys or even micro-Janskys. So you can imagine radio sources are not that strong. So a typical radio telescope, it gets about 100 minus dBm in terms of power, in terms of log scale. It is 100 dB minus 100 dBm of power, which will take basically about 1,000 years just to get 1 millijoule of energy. When you're holding your cell phone, you're actually spending more time, you're spending more energy, which is greater than 1 millijoule of energy. But one radio telescope will take 1,000 years just to collect 1 millijoule of energy, which is so small amount of energy. So, but still we are able to do so much with it. We are able to do such beautiful science with it. So we have to increase the sensitivity. Sensitivity is essentially what is the minimum amount of energy that can be detected. So to do this, we go for large collecting areas. We have to increase the collecting area. We have to increase our bucket size so that we are collecting more and more of such energy. We can have larger bandwidths. We can observe over longer durations. We can have better electronics which doesn't have noise. So as the noise of the system increases, sensitivity of the system decreases. So we can have a better and better electronics so that our instrument is sensitive enough to detect such feeble sources of energy in the sky. And now we are little moving into more of mathematical approach here, but more than mathematical, I would give you a visual approach. So just to understand how an antenna works, what antenna receives, this is one diagram, one graph is there, which is basically telling you if you have a uniform illumination, which is basically, this is your antenna. Let's say you have an antenna which is like a rectangle. Here you don't have antenna, here you don't have antenna, and here you have an antenna. So it's like a uniform illumination. Now, what this antenna sees in the sky is this how it will look in the sky. This is called as electric field or a far field pattern. So, and this is basically a sinc function, sin pi by pi function, sinc function. Anyone can guess what is the relationship between a rectangular and a sinc function? Just if you can put in chat box. What is the relation between this? What gives you sinc when you have a rectangular function? Exactly, someone answered Fourier transform. Exactly, that is the correct. So Fourier transform when you have a rectangular function, the Fourier transform, it is a sinc function. So basically, far field pattern of any antenna is the Fourier transform of its aperture. So if you have a rectangular aperture, you will get something called a sinc function as electric field pattern, and which will convert it to power, which is basically square of it will give you this. So this is the power pattern of this antenna, and power pattern is in popular terms is called as beam. So this is the beam of the antenna. This is how your antenna is looking in the sky. So to put simply, if you have a source in the sky which is in this position, you will receive something. But as it moves away, you will not receive anything. So the source will be detectable only when it is in this position, which is in the beam. So within the beam only you can detect a source. If it moves away from the beam, you will not detect it. So this is what is known as beam of an antenna, beam of a radio telescope. And just putting this, yeah. So putting this in terms of a parabolic dish or antenna or a radio telescope. So if you have a radio telescope, this is how its beam will be looking like, which is again essentially a far field pattern or a power pattern of this kind of illumination structure or aperture. And this is what your antenna beam looks like. This is what your telescope is looking in the sky. So whenever a source, this is a sky brightness distribution, or I can call it, there is a source here which cannot be detected here, but which will be detected only here. If it is here somewhere at other direction, which will not be detected. Only when it is in the beam, we will be detecting it. So, and as you can see here, it is falling down. So around half power, we call as a half power beam width. From the top, if we come around half power, is known as half power beamwidth point, and half power beamwidth point is given by an equation called as lambda by d. Lambda is the wavelength, and d is what is basically diameter of this aperture, which is the d. We call it d. So lambda by d is the half power beamwidth, or in other terms, we call it resolution. So angular resolution is the ability, as I was mentioning. See, any source which is only present in the beam will be detected, which is not in the beam will not be detected. So this basically defines what is the resolution of your telescope, what your telescope is seeing, what is the minimum angular separation that your telescope can detect. So this equation is this resolution is given by lambda by d. Lambda is the wavelength, d is the aperture, and is the in terms of radians. So you can do a quick calculation. So if you have let's say an optical telescope, which is around, let's say 12 centimeter, it has a length of 12 centimeter. Its resolution for around 600, which is in between our optical wavelength, is 1 arc second resolution. 1 arc second is you have 1 degree, you divide in 60 parts, you get 1 arc minute. You take 1 arc minute, divide in 60 parts, you get 1 arc second. So 1 arc second is a very, very, very small angular resolution with just 12 centimeter of an aperture. Of an optical aperture, you will get such a good resolution. Now, radio are longer wavelengths. So you can imagine your same resolution. To get same resolution, if you are increasing your wavelength, you need to increase your aperture size also. So radio wavelengths are size of around millimeters to kilometers. Now to have same arc second resolution, which you are able to achieve only through 12 centimeter using an optical telescope, to get same resolution using a radio telescope, you need around 100 meters to around 100 kilometers wide aperture, which is simply not possible. It's not practical to build a telescope which is 100 or 1,000 kilometers wide. How can it do it? It is not practical. But still, how we are able to get this? Because to function, to at least get a resolution which is closer to the optical resolution, you need such big kind of aperture. You need big telescope, but which is quite not possible. But how we are doing it? Still we are doing it. People are doing it. We are doing such wonderful science with it. Then how is it possible? So this is the quest for the resolution, the search, the need of resolution, which basically the answer for that, the solution for that, came through a something called as interferometry. Interferometry it's a thing which was used by optical people only. So, and optical people, they were using this interferometry, and it was adopted by radio astronomers. So just to give a basic idea of interferometry. Now, what is interferometry? Many of you might have learned about this, seen this experiment, seen videos of it, or actually performed this experiment, which is known as Young's double slit experiment. Now, in Young double slit experiment, what we do? We have a monochromatic light. We have 2 slits here, and these 2 slits will generate two wave fronts, which basically will add coherently to give bright light and there will be destructive interference to form dark lights. So together, this kind of pattern will be seen on the screen, and which is known as fringe. So when we have such two sources, two coherent sources of light, when they interfere with each other, you get such kind of pattern, which is known as fringe pattern. And further things is that if you increase the distance between the these two slits, what you notice is the fringes are actually getting closer and closer, and these things you notice in this double-slit experiment. But what optical inventors who were working with optics, what they did is they used this concept and built something called interferometer. So this is a basic idea of Michelson interferometer, which is used to study optical wavelengths. What is happening here is you have a laser light, a monochromatic or quasi-monochromatic laser light, which is split into two, which goes into two different paths and then reflected by mirrors. And then again, it comes back and is combined on a screen together. When we combine again, it will give rise to this interference pattern. So with this, we study this interference pattern. Now, as you can guess, these two paths have to be exactly matching with each other. So that when these signals are coherently added, they will exactly have the same path traveled by these two different waves. If there is any minor change in this path, what we get is there is a change in this interference pattern. So this was used to study surfaces of different mirrors. So what they can do is they can put an object in test here. So when object in the test is kept here, because of how the surface is, there will be actually changes, the little bit path changes in this light path. And when this interfere, there will be changes in this interference pattern. So based on this, you can study what is the surface properties of mirrors and all. So this was used for this kind of studies, but as radio astronomers adopted it and made into something called as radio interferometer. So now this is the basic of a radio interferometer. We have a 2-element radio interferometer where you can understand is let's say there are two antennas. Now we have two antennas which are spatially separated. This is not a big antenna, but we have two small antennas which are separated by a distance b, which is known as baseline distance b. Okay, so these antennas are separated by distance, and there is a source here in the sky which is at infinity distance. So at a source and infinity will basically give you a parallel wavefront. So now a parallel wavefront is coming. Now you can see that this parallel wavefront will reach this antenna first and this antenna later. There will be a time delay between these two signals which are received by this antenna, which if theta is the angle between the zenith and the source, we get the part difference to be b sine theta. So there is this part difference happening. And what we do is we combine this, we multiply these two signals and then integrate over time, which gives rise to this fringe pattern, which we saw which we saw here. Similar, now instead of two slits, we have two antennas which are recording two coherent signals, and when we correlate them, which we multiply and integrate for some time, we get something called as fringe pattern, which will look something like this. So we are having this fringe pattern because of this kind of antenna. So now I'm giving you a mathematical approach to it. Also, there is a small derivation. Those who are interested in more mathematical approach of how it is done can look more into it. So let's say you have two antennas which are receiving signals which are sinusoidal signals which are given by cos 2 pi omega t, where omega is the frequency, and v2 cos 2 omega t. Now, and tau is the geometric delay, which basically this antenna, as I mentioned, there was a delay in that, which is basically given by this tau. So now tau is a geometric delay, which is b sine theta divided by c. C is the velocity of light. And when you multiply these two signals and integrate over a time period of t, I'm not going much into detail how this derivation is done, but you can simply see using simple formulas of cos A, cos B, you can find this. And when you integrate, there is a condition that this integration time t is greater than the velocity. Omega is the velocity here, so greater than the one inverse of the frequency. If you integrate over this time, all these other terms will essentially turn out to be 0, and you will be left with this final term, which is cos of 2 pi omega t. Now in omega tau, cos of 2 pi omega tau, and tau itself here is, again, as I mentioned, is b sine theta. So it's a cosine of a sine kind of signal which is coming here, which if you plot, you can if anyone's are good in coding, you can simply put this equation in any MATLAB or Python, whatever language you're familiar with. You put this and you can get this kind of quasi sinusoidal pattern, which is not exactly a sinusoidal, as it is a sinusoidal of a sinusoidal. You will get this kind of pattern which is deviating from a sinusoidal, and when multiplied with individual antenna patterns, you get something like this. So now this is the fringe pattern that I was talking about that you are getting. And now here the resolution of this setup is defined by this, the whatever you are having, the central fringe here. This will define your resolution, where instead of previously we were talking about how the antenna's electric pattern is looking in the sky is defining the beam of the antenna. But now beam of the antenna will be defined by this structure, because if a source is present here, then only it will be detected. Here, if it is present here, it will not be detected. Again, if it is present here, it will be detected. If it is present here, it will not be detected. So the resolution is again lambda by d, where d is now not the aperture itself, but the distance between. And now you can guess. You can go far and far and far. You can put the two antennas farther and farther away, so that the fringe pattern will start coming closer and closer and closer, and you will have better and better resolution. So that is the essence. That is this is the basic concept of radio interferometry, where now not the individual antenna diameters or their apertures, but the distance between the two antennas defines your resolution, and then you can put them very, very far away to get a very good resolution. This is how interferometry is working. And now I'll quickly tell you how the images are made. So instead of 2 elements, let's say now you have an n element interferometer. And so you will have n into n minus 1 divided by 2 different unique baselines, and or something called as UV samples. Now UV sample is basically, to simply put, we are the plane in which we have kept our antennas. We call them as like UV planes. This is the baseline. This is the baseline plane or UV plane. So let's say you have 2 antennas, so you will have two UV samples, and this is the fringe pattern. This is the Fourier transform of this, what you are getting here. This is the fringe pattern you are getting, and you can see if the orientation changes, this orientation will be also change. So based on where the two antennas are located and what is the distance, you get this pattern. And now you start adding one and another antenna. What will happen is basically superimposition of all these different interference patterns together will give rise to such kind of interference patterns which are looking in the sky. Okay, so you are having three antennas. You will have you will have 6 different samples, and you will get this kind of interference pattern. If you have 5 antennas, you will get this kind of around 20 samples you are having, and this kind of interference pattern you get in the sky. So as you keep increasing the sample, you are basically filling the UV plane. This is U, this is V. You are filling those UV plane, and your interference pattern will keep on adding and adding and adding, and basically it will give you a combined effect of all these fringes together. So, and now this is basically used for imaging. Now what we are having is, as I mentioned, we are having UV plane. UV plane is the plane where we have placed our antennas, and we have something called image plane. Image plane is what is we are trying to image. It is the sky plane. Now it will have some brightness distribution that we are trying to image. Let's say there is some source here that we are trying to image. So it is in the image plane, and using our antenna, which is in UV plane, that we want to measure, which there is a relation between these two, which is given by Van Sitter-Zerniger theorem, which basically tells that what quantity you are measuring here, the correlations that you are measuring between these two antennas, which is known as visibility function, which is a complex quantity. That means it will have an amplitude as well as a phase. So when you record this, you're actually recording Fourier transform of the sky brightness distribution. Of course, this is a little approximation. It is not exactly, but just for the sake of simplicity, I'm not going much into mathematical explanations here. But what is happening essentially is the visibilities that you are recording. The visibility that is what recorded by this set of antennas is essentially a Fourier transform of the sky brightness distribution. So now you can imagine, if you want the image of the sky, what you need to do is you need to do inverse Fourier transform of what you have recorded. So this is how basically imaging in radio is working. You have different sets of antennas which are essentially recording different Fourier components of the sky. You record this and you combine this together, and you do inverse Fourier transform, and you will get the image of the sky. Now you can understand this is it's not, it's you are doing sampling here. You are putting points in UV plane. More the points, better the image. If you can fill this UV plane better and better with more and more number of points, you will have a good representation of the sky. So to do this, there is a concept of aperture synthesis, where what we are basically doing is, you have, let's say you have a baseline of 25 kilometers. That means you have placed two antennas which are 25 kilometers away. It is essentially like you have made an aperture which is of 20 kilometers diameter. So you have synthesized an aperture. There is no actual 25 kilometers aperture here. You don't have a lens which is 25 kilometers, but you just have two antennas which are 25 kilometers away from each other. And when combined with the signals from there, when correlate signal from them, it gives you resolution which is similar to a telescope which was 25 kilometers in diameter. So this is the concept of aperture synthesis. And as I mentioned, these are samples. The more samples, better the image. So now you need to fill more and more points. So what you can do is you can keep more and more antennas in between, so that you are having better UV coverage, so that you are having a better image when you do the inverse Fourier transform. But there is another technique which is called as Earth rotation synthesis, in which what happens, as Earth is rotating, we know that Earth is rotating with about 24 hours of period. So as Earth is rotating, what sky sees, the projection of these antennas, the baselines between these two antennas, will essentially keep on changing as a function of time. So you are actually feeling different points as the Earth rotates over this time period. So you are feeling more and more points, and this will give you better and better image. So this is called as Earth rotation synthesis imaging, and this technique was given by Martin Ryle, who won Nobel Prize in Physics in 1974 for development of this technique. So this is how Earth rotation synthesis is working. As you can see, let's say you have some UV samples which are giving you this kind of fringe pattern in the sky. Now you allow the telescope to observe for more time. What will happen? You can see these points will get little bit broadened. You are essentially observing little bit more points. As it goes away, as it goes time, more and more time, you are observing more and more such UV samples, and you are having this kind of beam, this kind of fringe pattern which is put in the sky, which you can remember. Ideally it should be only, there should be a center point, and everywhere else it should be zero. Nothing should be there. But everywhere, but as it's an approximation. We are sampling. We are not putting all the points. We are just using some points. So it will have this kind of structures which are coming here in between, which is called as dirty beam. So astronomers use this term called as dirty beam. So this is the dirty beam which is formed because of your radio telescope in the sky. Now, how to make image out of this? This is the beam, but to make the image, as I mentioned, you have to do, according to Van-Sitter's-Zernike theorem, you have to do a Fourier transform. You have to do inverse Fourier transform of the visibility function. So you get the visibility, and you do inverse Fourier transform, you will get that image. But this image is not just an image; it is called as dirty image. Dirty image means the image convolved with the beam pattern itself. Now, this beam pattern itself will be impregnated in your image, and you have to remove this pattern to get the actual image of the sky. So what you do is you have to clean this dirty image, which is basically the algorithm is called. So there is an algorithm called clean. So clean algorithm, what it does is it cleans this pattern which is there in the sky, and basically only gives you the object in the sky, which is the radio source, the celestial object that you wanted to image. So from this kind of structures, which this kind of putting this from image plane to UV plane, just doing a Fourier transform and doing a deconvolution with the fringe pattern, you can get the image. And this is how basically radio imaging is working. So whatever the radio images you have seen so far are done using this technique. Of course, I have simplified it to a great extent. There are a lot of details and further steps in between, but just to limit of the time, I'm just putting it in simple terms. So this is how basically a radio image is made. Now, there is a technique called VLBI, very long baseline interferometry, which is your Event Horizon Telescope was basically working on. Now, as I mentioned, you increase the distance between the two antennas, you get better and better resolution. And so you can go to different countries. So they have put these antennas in different countries or in different continents, and they get basically a telescope which is the size of the Earth itself, and which was used to image this which is the black hole in the center of Sagittarius Sagittarius constellation. There is a center. At the center, there is this galaxy. At the center of this galaxy, we have this supermassive black hole, which was imaged by this Event Horizon Telescope, and this is the image which was made using this VLBI technology, very long baseline, where you get very good resolutions. So this is these are some of other radio telescopes which are there operating presently. Arecibo telescope is not operating now, unfortunately. But what you can do is you can go further in detail of this telescope. You can understand what frequencies and what configuration these telescopes are there. So these are the different telescopes. And also in India, we have a good radio astronomy community, which basically started with TIFR, Tata Institute of Fundamental Research, which was established in 1945 by Homi Bhabha. Now, during this time only, he saw that radio astronomy is the field that we need to get into. So, under the leadership of Dr. Govind Swarup, who recently passed away, a radio astronomy community was established, and first radio telescope in India was established in a place near Mumbai called Kalyan. In Kalyan, they placed these radio antennas and started the radio astronomy in 1963. And soon another radio telescope in Ooty, which is known as Ooty Radio Telescope, was established. So, and then in 1976, Gauri Bidnoor, the place where I am presently now, from where I am giving you this talk, another radio observatory by collaboration between Indian Institute of Astrophysics and Raman Research Institute. They came together and started this Gauri Bidnoor radio observatory for low frequency observation. And in 2000, another big telescope which was launched, which is known as Giant Meter Radio Telescope, which is in a place called Narangao Kodat in Pune, which is a huge antenna. Each antenna is about 45 meters, and there are such 30 dishes kept around 30 kilometers wide area. So it's essentially a radio telescope, essentially a telescope wide of like capabilities of having a telescope which is 30 kilometers wide. So this is this is one of the most, or the most sensitive radio telescope now presently on Earth. We are using this telescope to do wonderful search studies, and this has helped in lot of scientific discoveries, including the one which I initially talked about. I talked about this gravitational waves which were detected using radio telescope. So in these studies also, this GMRT was actually used, and this we should be really happy that our Indian Indian scientific community also involved in this kind of studies. And to know how exactly it is done, I just briefly give you another story first. This started in 1967. 1967 is just about 30 years after the discovery of radio astronomy field. This time our protagonist is a young scientist, a young graduate student called Jocelyn Bell. She was a graduate student at Cambridge University, working under Professor Anthony Hewish, and she was working on observations of something called as quasars. So quasars are quasi-stellar objects, which are like, again, very strong radio sources which are observed to understand the effects of scintillation. So they were trying to understand this effect, and during one such observation, what she noticed is a train of periodic pulses which were highly regular. Now, this kind of observation was never done before. They had never seen such thing, where you are getting incredibly regular pulses from the sky. And of course, initially they thought it might be some interference, which and it was rejected that, okay, let's not go into it. It might be some interference, because no object in space can generate such highly regular pulses. So, but Jocelyn Bell persisted. She told no, she need to study it, and she kept on observing this and kept on, and later it was actually found. Initially they even thought that it might be because of some aliens, so they called the signal as LGM, little green men. So they thought this is the signal sent by aliens, because no natural process can produce such a incredibly regular pulses. So they thought it must be aliens, they are having some instrument and they are sending the signal towards, so they called it little green men. But of course it was later found out, it was later more studied, and it was a pulsar. So she had discovered a pulsar, and this was the paper that came in 1968. And for this discovery, Nobel Prize was given to her supervisor, Anthony Hewish. Unfortunately, yeah, but she got the recognition for as the first one to discover a pulsar. Now, why I'm talking about pulsar? Because to understand the gravitational waves which are recently detected, we need to understand pulsars. So pulsars are actually extremely dense and rapidly rotating neutron stars. So at the end of a life, at the end of a star, they either become based on mass, they become white dwarfs, or they become neutron stars, or they can become black holes based on its mass. So when we have neutron star, it's like they are so dense that electrons and protons are coming together to form this neutron. It is so dense. So it is so dense that even they have radius of only about 10 kilometers, and this 10 kilometers radius, they have mass of about 3 solar masses, which is insanely dense. If you take 1 tablespoon of this object, it will weigh around like Earth. So this is the incredible density that we are talking about, and they have huge magnetic field, which is of the order 10 to the power 12 Gauss. And so this is how they emit signal. If you can see, whenever they are from its north and south poles, they are emitting this radiation beams, and whenever this beam comes in our direction, you see this kind of pulses. This is how a pulsar signal is detected. Whenever, so this is like a lighthouse, whenever this pulse will come in our direction, we will see this pulse. Yeah, correct. So this is the pulse, this is the train of the pulses that we are seeing, and the time period between these two pulses is known as pulsar period. Now this pulsar periods can range from 1.4 milliseconds to around 23 seconds. Now the fastest node is 1.4 milliseconds. So can you imagine, it is rotating about 1,000 times per second. Which is like a unimaginable rotation speed. So in 1 second, it rotates around 1,000 of time, and this type of objects are known as millisecond pulsars. And interesting thing is, these periods are incredibly stable. So we know exactly what is the period, and over a long duration, this period stays stable. So we can know exactly when the next pulse is supposed to arrive. So that's why they are like clocks in the sky. So we use these pulsars as clocks, because as they're having they have such a stable periods, we can use them to actually calibrate our clocks. And just to little bit deviate, now I talked about pulsars. Let's talk about gravitational waves. Gravitational waves are ripples in this space-time. These are whenever these two supermassive black holes or two neutron stars, they are rotating about themselves, they generate ripples in the space-time. So this is the fabric of the space-time, and these are the disturbances, which is known as gravitational waves, which are detected using something called as LIGO detectors or laser interferometer gravitational wave detector, which is similar to the Michelson interferometer I had shown some time back, which essentially working is there is a laser beam which is splitted and it goes into 2 paths, and there are 2 mirrors kept, and when they come back, they go into different path, and then on the screen we see an interference pattern. Now imagine if there is a gravitational wave coming, which is the disturbance here in the space-time itself. Because of this, whenever it is traveling, the path length itself will change. And as I mentioned, if there is a slight changes in the path, there will be changes in this interference pattern. So through the changes in the interference pattern, we can measure if a gravitational wave is coming or not. And this kind of setup is an incredible setup in Hanford. This is about kilometer long arms they have, where one mirror is kept here, one mirror is kept here, and at the center you have this beam splitter, and it will go and it will form this image. This kind of LIGO detector, but it can detect gravitational waves which are of Hertz level. That means the frequency of this is around Hertz. But there is another concept of gravitational wave background. Now, gravitational wave background, what means is, there are the supermassive black holes which are merging throughout the universe. Everywhere these are merging, and when combined, the gravitational wave from all of this supermassive black hole combined together should give rise to a gravitational wave background, which is superimposition of all these waves together, which will be having frequency of nanohertz. Now, nanohertz is 10 to the power -9 seconds, which if you 10 to the power 9 seconds, so 10 to the power minus 9 hertz, when we convert into time scale, it will be 10 to the power 9, which essentially it's like a wave which is traveling over decades. It will take about 10 to 15 years for that wave to pass. So now such kind of low frequency gravitational waves will not be detected by such LIGO detectors, because it can only detect hertz, but we need to detect nanohertz. So what we do, and for this exactly the pulsars come to the rescue. Now what we have is essentially something called as pulsar timing array. So pulsar timing array is the one which gave this detection, and how it essentially works is we have array of millisecond pulsars, which I had mentioned that they have very regular time periods between these two pulses. So we monitor them. So there is a misconception that pulsar timing array is the array of telescope. It is not array of telescope, but it is the array of pulsars in the sky that we keep observing. And we are observing these pulsars. Let's say this is the Earth, this is the space time, and we are having different pulsars which we keep regularly monitoring. Okay, so now from this pulsars we are having regular pulses. From this pulsar also we are having regular pulses. So we are observing multiple such millisecond pulsars, which we know what is the period between these two pulses, and so we model them. So we model the time of arrivals, the TOA. We model the time of arrivals of such, which is not an easy thing to do. You need lot of knowledge of other things, such as we need to understand how the Earth is rotating. We need to understand how the Earth is revolving around Sun, how the solar system itself is rotating. We need to understand the effects of Sun. We need to understand effects such as planets like Jupiter, which is also affecting the gravity around Earth. So all these effects, we model the interstellar medium which is present between the pulsar and the Earth. We need to model it to incredible precision. And when we do this, we essentially can predict when the next pulse is going to arrive. So we basically make a model of this time of arrivals, and we actually then, based on the real observations, we compare when this pulse should have arrived to when it is actually arriving. So this is called as timing residuals. So based on this timing residuals, we can see if are there any changes when we remove all the known effects. We have removed all the known effects of the interstellar medium. We have removed effects due to Sun. We have removed effect due to Earth's rotation. We have all other atmospheric events. Everything you have removed. There should not be change in the pulse arrival time. But still, if there is a change, which will be because the gravitational wave itself is traveling through this medium. Now let's imagine there is a gravitational wave coming. Because of that, the space between the pulsar and Earth itself will get shrink or expanded based on the gravitational wave, and there will be changes in the time of arrival. And based on that, if let's say if there is a gravitational wave coming in this direction, first pulse, this pulsar will be affected, then this pulsar will be affected, then this pulsar will be affected. So you can find the direction of this gravitational wave. So this is how pulsar timing arrays are working. And there is a collaboration called International Pulsar Timing Array, IPTA, which basically consists of Australian, European, and also Indian pulsar timing, which includes institutes such as TIFR, RRI, IIT Roorkee. These are the institutes which are included in Indian pulsar timing array. So all this came together, and they observed over 60 millisecond pulsars over 15 years of time. As I had mentioned, this wave itself will take about a decade to pass. So you have to keep monitoring this pulsar. And what they did is, using this, they observe. So this is the that universe that we are seeing, and there are these different pulsars which are spread over our galaxy. So all the pulsars that we are observe are our galactic pulsar, which are within our galaxy. So we observe these pulsar which are in different directions. So essentially, you are making a LIGO detector of which is spread over entire galaxy. So you are making a galaxy-sized telescope, and you keep observing these pulsars. And over the 15 years, what you do is you correlate the timing residuals. The timing residuals, as I mentioned, is the difference between the time of arrival that was expected and the actual time of arrival of this pulsar. So you get this residual of these different pulsars which are spatially located in different directions, and you correlate them. So here, what it was predicted. This is something called as HD diagram. So Helsings and Downs predicted this. So if you correlate these pulsars which are angularly, which have a certain angular separation between them, and you correlate them, this is how you should expect if there is a gravitational wave background. If there is a nanohertz gravitational wave background, this is what you should expect. And the recent observation results that came from this IPTA collaboration gave this kind of results, where you can see black one is the predicted and the red ones are the actually detected one. So you can see it is closely matching with what was predicted. So this is essentially the first evidence of a stochastic gravitational wave background, which is a very prominent discovery in this era, around 15, using only 15 years of time. And as you can see, it is not a something which was done quickly. It took 15 years for hundreds of people to work and find these timing residuals and closely monitor these stars over different types of observation spread all over the world. And they did this, and they were able to detect this nanohertz gravitational background. So this is essentially what we have come towards now. And what is upcoming? Upcoming, we are having something called as SKA, Square Kilometer Array, which is supposed to be the biggest radio telescope ever made. It will have, it is so big that it will be spread over 2 continents. Half of it will be put in Australia, half of it will be put in Africa. So we are having this upcoming radio telescope, which whatever studies we have done so far, this kind of square kilometer array size aperture telescope will give you incredible sensitivity, and it will give you insane resolution, which will be used to do further kind of studies, which can reveal so much about this universe. So from 1931, when the radio astronomy field was discovered, we have come not even about 80 years. In this 80 years, we have done so much. Like the scientists and the engineers and inventors, they have developed so many techniques that we are able to see this universe in a completely different kind of way, and we are finding so many different new things about this universe. So the actual thing is that you should ask the right questions and you should expect spectacular answers. So with this, I like to stop, and these are some of the sources that I have used for my talk. Please feel free to email me or get in touch with me if you want to further have any discussion. I'm just open to any questions now. Please feel free to ask. Thank you.
Thank you for that wonderful session, Kshitij. So we have a lot of questions from the chat box. I will read one by one.
Sure.
Yeah. So yeah. So one question is, how do I proceed to study radio astronomy with an engineering background, and what research is going in cosmology with radio telescopes?
Okay, so first I answer the second part, regarding cosmology. So you might have heard this word called CMB, cosmic microwave background radiation, which is another serendipitous detection done using radio telescope by 2 engineers. So it actually matches with your first question also. So 2 engineers who were working at Bell laboratories, they were observing this. They had built this big horn antenna, and they were observing this observing the night sky, observing the sky story, and they noticed that there is a constant signal coming from all the direction, which basically is the cosmic microwave background radiation. So in terms of cosmology, radio astronomy is very much useful. All this cosmological aspects, where cosmology is study of the universe as a whole. We study big scale structures in cosmology. So when we want to study how the universe is expanding, or what are the background radiations there, so to study that, we need to study the galaxies which are very far away, and we need to understand how they are moving away from each other, or how they are moving away from us. And to do this, we basically study something called as Doppler shifts and all, which basically tells us how they are going away from us. And in this case, the radio telescope, which can see with this incredible, which is very high resolution, it can see this far away galaxies, and we can see how they are moving away and how the universe is expanding. So that gives you the study of cosmology. And to give context for what you need, like from engineering background, so radio astronomy is directly extension of, I would say, engineering. So it has more engineers working because radio astronomy, it involves a lot of electronics, it involves a lot of data processing, it involves a lot of data analysis, which is essentially what engineers are trained to do. So you can do masters or your PhD in instrumentation in electronics, which can, through this, you can lead into the field of radio astronomy if you are interested in instrumentation. Yeah.
Okay. We have another question. In regular photography, lenses cause so many different effects like diffraction, chromatic aberration, etc., which we need some processes to enhance or reduce it.
Can you repeat the question? Wait, is this question in the chat box?
Yes, yes.
Wait, let me go through because
it's pretty long, it's at 8:06 p.m. So he says that what kind of effects do we will we see in different radio telescope arrays?
Okay, wait, okay. So exactly, so exactly similar kind of effects you also have. So whenever a radio signal is coming, so what we have is we have chromatic aberrations or diffractions, as you have mentioned. So it is like basically different when a optical wavelength is coming towards you, optical signal is coming to you, it is being diffracted by something which is present in between, or also even something called as different frequencies are behaving differently, which is basically a chromatic aberration. So different frequencies being focused at different points. So in radio astronomy also, what we have is we are observing at different frequencies. So I mentioned something called interstellar medium, which is present between these objects that we are observing and our Earth. So this interstellar medium acts differently for different frequencies. So these different frequencies will be delayed differently. They will arriving differently at different times. So you need to correct for this effect. So this effect is not a dispersion. So similar to optical, we do have similar effects in radio also. So we are having something called a dispersion. We are having something called a scattering, which is like diffraction, which is because of different obstacles, your signal will be scattered. Hello?
The switch was
Hello? Yeah. So this is, so in radio also we do have this effect. So any what is the next question?
Yeah. So there's another question. Is it correct?
Hopefully I was able to answer the previous question. Yeah. So next one.
Yeah. So there is another question. Is it correct to a sharper beam, less half power width is better for resolution?
Exactly. Yeah. So the sharper and sharper beam, you will have better and better resolution. So you need to either build a bigger and bigger telescope, or you need to pick bigger and bigger baselines. You need to keep the antennas very far away so that your beam width will be very sharp. Your beam will be very sharp. So you will have better resolution. So that is the concept of interferometry, where we are putting antennas farther and farther away.
Okay, there is another question. Could you please repeat difference of UV sample and baseline, and why is it n into n minus 1 whole by 2?
Okay. Let me go back. Yeah. Okay. Yeah. So UV, when I mean, let's say you have two antennas. How many baselines you will have? You will have one baseline. That is the distance between two antennas. If you have three antennas, what are the different combinations you can have? That is, you can have three different combinations. You have one and between one and antenna number 1 and 2, antenna number 2 and 3, and antenna number 3 and 1. So you have three. So the number of unique baselines that you can have is n into n minus 1 divided by 2. It is just basic permutation and combination. What is the different combinations that you can have with n number of antennas? So as you can say, if you have five antennas, so you will have 5 into 4 divided by 2, which is 10. So which you can have 10 different baselines between 5 antennas. So all the different combinations, 1 and 2, 1 and 3, 3 and 2, 3 and 4. So this gives you the number of baselines. Now, number of UV sample is the vector, basically vector between these two these antennas. So now whenever vector has a direction. So from 1 to 2 you have one direction, but also antenna number 2 to 1 you have another direction, which is basically just negative of the what you had. So so you are having two vectors now. So that's why you are having more double UV sample. So here also you can see it is just UV samples are just like mirror image of each other. You can see here you have three samples. Now just mirror image of each, which are just the negative values, because vector will have direction. And that direction can give you another sample in this UV plane. Hope I was able to answer this. Any doubt or any question?
Okay. So there's one question. It says, how is signal is separated out from coming out through observed source? Basically, when the signal is coming from the source to the radio antenna, there will be so many obstacles. So how
Right.
are we not picking up something artifact of that obstacle? Like, how are we separating that out?
No, so what happens is, in between, if some obstacle is there, that is the advantage of radio astronomy, that the wavelength is very huge. So it is not affected by the objects which are smaller than its wavelength. So dust particles or any other particles which are present. If there is something which is completely blocking it, you will not receive it at all. If there is let's say there is a planet coming in between something which is not there, you will not at all receive it. But if there is small obstacles, the radio waves still pass through it and it will come to you. So it is not affected by whatever the atmosphere is there, or whatever dust particles are there, or whatever any other small obstacles are there, or even clouds. On Earth we have these clouds. So even if clouds is there, it is not bothered. We can still see beyond clouds because the radio waves are not affected by it. As they are having longer wavelengths, they can simply just pass through it. So that's why they are not affected by the obstacles. Of course, it will have, like, if there are larger objects, which will have a scattering effect. So the gravitational, your radio wave will be scattered, and in essence, then you will see the effect of it. So there will be multiple scattering which will be happening now because of, let's say, there is a big object. Through edge of it, now this radio wave will come through you. It will have multiple reflections. So now when combined, you will have something it will call as scattering. Now scattering will essentially result in image being fuzzy. So you will have blurry image. So when you should supposed to have a very sharp image, there is an obstacle in between. It will result in that image being blurred or little bit fuzzy because of effect of scattering. So it will be broadened. So this is the effect of scattering. Yeah.
Guys, I think you can unmute and ask the questions now. There is one question. Is there any single reason for 21 centimeter neutral hydrogen spectrum?
Yeah. So there are different types of antennas. I actually didn't cover that part here because of the time limitation. But antenna itself is a very broad field in itself, because it has it is used in communication, it is used in radar, it is in defense. So many things antennas are used. So there are different types of antennas. I just, during this talk, I was just mentioning about this parabolic dish kind of antennas, but there are different types of antenna. Which another type of antenna is horn antenna. So horn antenna, which looks like a horn, and which is based on its dimension, it will predict the frequency that it is receiving. So 21 centimeters. So when we say 21 centimeter, it is the wavelength of the signal that is coming. So 21 centimeters is the wavelength. So according to that, you can have the dimension of the horn antenna, and then you can receive those signals. So for 21 centimeter, usually or most often you use an antenna called as horn antenna. So you can read more about it and try to build your horn antenna by your own also.
Okay, there is one question. Does it make sense to place any antennas on Moon or Mars, etc.?
Definitely. Why not? So as I mentioned, for better and better resolution, you need to have antennas which are farther and farther away. Now on Earth, you can just are limited by what is the maximum distance of half of the circumference of the Earth, right? That is the maximum distance that you can have between 2 points on Earth. Now let's say I keep one antenna on Earth and another antenna on Moon. So now you will have huge baseline, which is actually in plan. There are actually some proposals regarding this where they want a space interferometer, where they want two antennas put in space, where one antenna put in Moon and one antenna Earth. So it can give larger baseline distances. So it does make sense, and there are work going on this kind of baselines, which will be like a Moon or even farther than that in future if possible. Yeah.
Okay, there is one more question. So Kritika, she's asking, I'm working in the instrumentation field, safety system. What can I do with PLC programming in this field? Can you give some ideas?
PLC programming, actually, I'm also not much aware of. I don't know how this is
Kritika, if you're
related to
here, you
previous
can
for me.
unmute and ask. Kritika, if you're here, you can unmute and ask.
Yeah, sure.
Okay, in the meantime,
PLC is like programmable logic control or something. I don't know what PLC is.
It's that is programming logic controller.
Yeah. Okay.
I'm working in like PLC programming for the safety systems. Like if you have a plant, you need a safety in that one. So likewise, where is the safety necessary in this field?
Okay, but I don't know how directly this will be related, but we do use lot of back-end receivers such as FPGAs program, which are field programmable gate. So we use FPGA receivers to record the signals. If you remember, I had mentioned that any radio telescope should have some kind of something called as receiver.
Yes.
Now that receiver is basically, you have something called as ADC, analog to digital converter,
Yes.
and now
Yes,
to process this we need FPGAs. So when we need FPGA, and on a FPGA we do VHDL language programming, and you do so if you are interested in that kind of programming languages, that you can then learn more of, and you can get in touch with me to understand more how that works.
Okay, but I have read in some AA notifications like in project position they are releasing. In that one, they are saying like PLC programming. Likewise, yeah.
Okay. So this is that will be for some other type of work, which is presently there is a new telescope coming called as TMT, 13-meter telescope. Which has a lot of electronics. So whenever we are having any telescope, it involves lot of electronics, it involves lot of processing, it involves lot of control processors, or we call as control systems. So lot of control system work goes on. So for that work, they will be definitely requiring such kind of PLC control work. So you can get in touch with them, and you can see if you can get any project or you can get any position there for this kind of work. So this is purely that is purely electronics and control system work.
Okay. Like how can I contact with that one?
I don't know exactly. They might have given some email ID or something like that, but you can check on the website itself. Let's not discuss more into this, because there might be some other question. But on the website and all, you can find appropriate contact links and everything there. So you can check the iap.res.in website. You can check.
Thank you.
Sure. Okay. Yeah.
Hello, Kshitij. Good evening.
Yeah. Good evening.
I'm sorry, I will have to circle you back on the radio wave propagation. So I read this, that usually when pulsars are reported, or any of their data is reported, there is a parameter called dispersion measure.
Exactly.
So I assumed that it is accounting for any kind of dispersion while the emission is traveling from its source to the radio telescope.
Correct.
But I got a bit confused here right now, because as you said, radio waves are hardly blocked by any other sources or affected by any other thing. So what is this parameter accounting for?
Exactly. Okay. So now I'm not talking about obstacles. So what actually is essentially happening is, when you are saying the medium which is present between our Earth and the pulsar, there is this interstellar medium which is called ISM. Okay, so this is the interstellar medium. Now this consists of lot of free electrons, and which are a lot of the plasma. So it's essentially a plasma medium between us and the source. Now I'm not saying these are affected in terms of like where they will just blocked by it. But what will happen, these effects are frequency dependent. So it is essentially like a prism. Like in prism, when you pass white light, at the output you get 7 colors. They are not blocked by it, but they just travel different paths. Right? So
Yeah.
So in this interstellar medium also, when let's say you have a broadband signal which consists of lot of frequencies. So when they're coming towards us, each frequency will be traveling differently, not differently in terms of the it is not going in different directions, it is not going away, but it takes more time to reach to us for different frequency. Lower the frequency, it will take more time. Higher the frequency, it will reach to us. So this is essentially the dispersion. So when you are having a pulsar signal coming towards, if you observe the pulsar at higher frequency, the signal will arrive you at faster. But when you observe at a lower frequency, it will come later. So this is the dispersion, and you need to correct for it. You need to basically delay the high frequency signal so that it will match with the lower frequency signal. So which is essentially the dispersion measure. So what dispersion measure, is called as DM. So DM is basically how many number of electrons are present between you and the source. It is integration of this number of electrons over the path length. So this basically gives you how these different frequencies are arriving. So they will not be completely blocked or going in some other. So that effect is also there, which is called as scattering. But what I'm talking about is dispersion. Dispersion is just different frequencies behaving differently. So it is, you can imagine like a prism. So your this itself, your interstellar medium is a prism in which your white light is coming, and then you get 7 colors. So similarly, now in time, this different frequency will be arriving. So if just to give analogy, if you send a white light, red light will be arriving at you at later compared to the blue light. So this is what is happening.
Okay. Just one follow-up question on this. So as you said, this is accounting for the distance. I mean, all the free electrons between the observer and the source. So for this, we need to know the distance of the pulsar, right? So do we already know that?
No.
Let's
so
say,
actually this is universe.
Yeah.
So we don't know the distance, but we can predict what is the electron density, and we know what is the dispersion measure. So you know the dispersion measure, which should be integration of the electron density or the distance. So you don't know the distance. That's how you find a distance. So we don't measure the distance directly. What we do is we find the dispersion measure, because we can now, let's say you observe at 2 different frequencies. You know what is the time difference between these two. And now because of this time difference of these 2 different frequency, you can know what is the dispersion measure. And from dispersion measure, you know what is the distance. So that's how it works.
Okay. Right. Thank you so much. That clears a lot. One more question. So I was hoping that you would also talk about how the polarization detection is working in the radio telescope.
Yeah.
So in the interest of time, can you just like guide me to any textbook or resource where I can rigorously learn how this is done?
I have mentioned the sources here itself. So you can see, if you can go through any of this source, mostly this book called Radio Astronomy by Krauss. It's like a Bible for radio astronomers. You can find a lot of information there. But just to give you a brief, see what is the polarization. Polarization is how your electromagnetic vector is arriving at you in what phase, right? That is essentially a polarization. It gives you the direction of the wave that is falling on it. Now, how an antenna works? You have an antenna. Let's say you have a something called as dipole antenna. So you have basically a metallic wire of some length. So now whenever a radio wave is falling on it, the electrons on top of it will vibrate according to the frequency which is falling on it, and it will give you the corresponding voltages. So that you're recording. So that is how antenna is working. So antenna is in between the electromagnetic radiation and your voltages. Okay. Now, if a radio wave is exactly falling on that antenna itself, on that length, you will get the maximum signal. But if that vector little bit changes, there will be reduction in the voltage that you receive. So now let's say you have an antenna which is some 0 degree oriented, and the wave is also falling on it 0 degree oriented. You will receive the maximum signal. But now the vector is 90 degree oriented, and your antenna was 0 degree oriented. You will not receive any signal. So your antenna itself is telling you what is the polarization of the input signal. You understood?
Okay.
So
So,
what is
all
yeah?
right.
So in
Yeah.
the in radio astronomy, how you place your antenna, your antenna itself will determine what is the polarization of the wave falling on it. So what you can do is you can keep two antennas which are together 90-degree oriented. So one antenna will receive the wave which is falling 0-degree oriented, another antenna will receive which is 90-degree oriented. And when you combine, you can find all these other orientations such as circular polarization, 45-degree polarizations, all this you
Right.
can find. So just using, so antenna itself is acting like a polarizer. Yeah.
Okay. So, okay, I got it. So, as you said, we would record this induced voltage, and this voltage itself will contain this information
Exactly.
fundamentally.
That is
in its,
one of the major
yeah.
advantage of radio astronomy, which you don't get in optical.
Okay.
In optical, you're having very high frequency. So you're dealing in terms of photons, and photons they are not telling you the polar. So you have to use polarizers. You will use different sets
Yes.
of polarizers to give you polarization. But the advantage of radio astronomy is that antenna itself is giving you polarization information. You don't need to
Okay.
use further
Yeah,
polarizer. Yeah.
that makes sense. Thank you. Thank you so much, Kshitij, for clearing all the doubts.
Great. Any other questions?
There are one more question in the chat box. So I have heard of software-defined radio.
Correct.
I can already guess there is a huge role in the radio astronomy. Could you give a tiny intro?
Yeah, exactly. So software. So whenever I didn't do much talk about what happens in the back end of a telescope. So I told like that we have some amplifiers, we have some filters, we have something called as ADC, analog to digital converters, which will do all this. And then there are further processes like where we are correlating the signal, or we are adding those signal, we are integrating those signal. Now let's say you have a time signal, which is like a voltage as a function of time, and you need to identify the frequency information in. So what you need to do, you need to do a Fourier transform. Fourier transform will basically tell you what is the information contained in the time varying signal, right? So all these processes are happening in the backend. So you are doing this. So now software defined radio, what it does is it will get just the raw voltages from the signal and do all these processes software. Like inside the software it will do, and then it will directly give you the output. So you are not having big equipments to do all this. So software defined radio will basically give you all this complicated things which are supposed to happen in hardware in software. So it's like a replicating hardware into a software, and it will do all these operations mathematically and give you the output. So that's how a software defined radio works. So SDR, so it's a software defined radio. It will do, there are processes such as mixing, there is a process called multiplications, Fourier transform. All this will happen in software, and so that your size of the instrument is reduced. So you can have like a pen drive kind of size of equipment just to record a signal, and all other things are happening in your computer in software. So that's how a software-defined radio works, and you can get it for a very cheap price. For about 5,000 to 6,000 rupees, you get a good SDR, and then you can do a lot of variety of things using it. Because now you can record the signals and you can do anything you want in software. There is a question regarding data size. Yeah, exactly. So data size basically depends on what is your integration time. So how fast you're recording the data. So if you're recording at very high speeds, your sizes will be increasing. But if you're recording at low speeds where that type of resolution is not required. So for example, when I'm observing some pulsars, I need a very good time resolution, because pulsar itself, the period is in terms of milliseconds. So you need to have sampling. So there is a big topic in radio astronomy called as sampling theorem. I haven't touched upon it, but you might already be aware of it. So we something called as sampling. So sampling, whenever you are converting an analog signal to a digital, how fast you should sample. It basically depends on the bandwidth of the signal. What is the information content? The information content is in the bandwidth. So just to give you like a basic idea, you need to sample at around twice of your bandwidth. So that is your sampling frequency. So it depends on what frequency and what bandwidth you're observing and what are the information rate that you want. So this will give you what are the sizes of the data. So we do have sizes which go from gigabytes to terabytes, and there are when this square kilometer array will be there, it will generate terabytes of data within seconds. So it's a huge amount of data. So lot of data science and lot of what is called big data kind of work is happening in this. So you can explore that also.
Is there any other doubts, guys? You can unmute and ask. Okay, I don't think there is any other doubts. Okay then, my audio is clear, right?
Yeah.
Just a confirmation. Okay, so yeah, thank you, Kshitij. Thank you very much for this wonderful session. You gave a very good introduction to
Thank you. Thank you.
essential techniques, and actually covered more than 2-3 techniques, I think. So thank you very much, and hopefully this will be very informative and helpful to people who are trying to pursue radio astronomy or exploring topics that they can pursue further. And guys, tomorrow there is another webinar by Rishabh Singha, who will be talking on interstellar space dust and how the interstellar space dust study is very important for galaxy evolution, stellar evolution, and how we can observe those interstellar space dust. So, and further things. So, kindly join the tomorrow's webinar also. And you can go to learn.nakshatra.com website and you can register the webinar for free and you will get all the notification emails. And thank you very much for joining, guys. And yeah, have a great evening.
Thank you. Please, anyone, if in having any further doubt, please feel free to contact me. I have given my email ID here. You can contact me for any other doubts or any discussion.